Research and development engineers explore new ideas and innovations. Their purpose is to solve customers' problems, to enable new capabilities, and to provide efficiencies to save their companies money. Researchers develop core algorithms, new platforms, and solve some really major technological challenges. One popular field of research and development is DSP, or digital signal processing. Digital signal processing is the mathematical manipulation of a signal, audio or video, to analyze, modify, or improve it. So when you're singing in Rock Band or Guitar Hero and it's detecting your pitch, giving you a score, well, that's a DSP technique called pitch detection. When a singer's in a recording studio and they're singing an incorrect note, well, the studio engineer can use pitch correction, such as Antares Auto-Tune, to automatically fix it. When you're adding echoes or reverb to make your voice sound bigger and fuller, well, those are also good DSP examples. Hardware products require lots of DSP, ranging from bread and butter digital signal processing, such as a graphic EQ on a PA system or a stereo system, to the DSP algorithms running inside of your guitar pedal or amplifier. Yes, there are mathematical models of tubes and circuits in guitar amplifiers. Well, this is awesome, so you can reproduce the sound of dozens of guitar amps all modeled on a single chip. Companies like Dolby and DTS have built entirely new markets, such as delivering surround sound in theaters and homes. Their algorithms enhance and compress multi-channel sound. Zooming out, R&D is about much more than DSP. It's about creating or improving new processes or technologies. Wireless speaker companies, such as Sonos, have invested millions in developing wireless, room-to-room audio transmission technology. Another example is the machine learning and music recommendation engines powering Spotify and Pandora. Those systems are based on data science and complex music information retrieval algorithms, which unleash the value of massive music catalogs and help understand the preferences of millions of users. Pandora and Spotify's tools enable us to search and explore all the world's music. The core algorithms are often seen as the magic of a product. When I use Shazam or SoundHound, I can hold up my mobile device and it will tell me what sound or what song is playing in the background in 4 seconds. Even if I'm in a loud restaurant, there are people talking in the background. Well, that's the magic of audio fingerprinting. Pandora's music recommendation engine, well, that offers a similar magic. In fact, the image stabilization algorithms built into modern digital video cameras or GoPros, that turns unusable video into award-winning content. Despite months or even years of R&D, these innovations might be only 5% of the total work required to launch the product. When we examine product releases across the entire media technology industry, the total development effort to bring these innovations to market is the other 95% of a product release. When I was entering industry, I thought that for Avid to create new innovations in Pro Tools, all they had to do was let me spend a few months working on some cool ideas. Well, that was before I knew about the other 95%. And what is the other 95%? It's a huge list of things. For example, the product development to explore the applications, the product line integration of your technology, the immense software engineering requirements to take your idea into something that's commercial grade, to make it robust to real-world challenges, to do the quality assurance, scalability, infrastructure, graphic design, marketing, legal, sales, tech support, so much more. The real cost of algorithm development is the following. It's the cost to integrate the technology, plus the cost to explore it, plus running some validations on it, bringing it into the company's infrastructure, testing it, releasing it, to keep supporting it, the opportunity cost for choosing this technology over other technologies, and the cost to remove it and end-of-line the technology. When you add that all up, it is significant. This enormous cost to commercialize innovations is why you often do not see huge research teams. Let's look at Adobe. They have between 50 and 100 researchers worldwide, out of 12,000 employees. Now, the innovations that those 50 to 100 researchers, that's supported by the rest of the 11,950 people in the organization. R&D projects in industry are different than in academia. In academia, 85% accuracy for an algorithm, that might be awesome, and that could be a very strong scientific journal paper. However, 85% for commercial uses might actually be horrific, unusable even. 90% might actually feel like magic and then create an amazing customer experience. But can you achieve that? Let's look at audio fingerprinting. For fingerprinting to function well, it needs to work in the presence of noise. It needs to work on many mobile handsets. The material that it's analyzing, that could be played back on a PA system at an airport or on your car stereo. The fingerprinting algorithm has to work on music that's loud or quiet, and there might even be people speaking in the background of it. It must be robust to be commercially successful, and it must be fast. How do they determine when the algorithm was actually good enough to ship? We're going to look at that in this session. Another example of how industry and academia expectations are different is in the scalability of an algorithm. R&D can be about optimizing computationally complex algorithms. Shazam has over 100 million monthly active users. Users query the system over 20 million times per day. Now, users expect the system to identify what track is playing in the background of a bar or restaurant in under 4 seconds. That's quite a computational challenge, and one in which an academic project would never be able to keep up with. During a recent panel discussion, a lead engineer at an audio fingerprinting company said, "I could give away the audio fingerprinting algorithm, the source code, all the patents, and we'd still be very competitive." The value is the years of large-scale search and retrieval, and the heuristics and best practices that we've learned from handling millions of queries a day. That's our real secret sauce. What separates some of the best research engineers and managers? Well, one consistent answer I've heard in our interviews: R&D engineers rise to the top when they realize the business value of their research products. How about another great answer? Researchers who make it to the top are the ones who've seen the products all the way to the end. Those are the folks who see something created in the lab brought all the way to market. In this session, we're going to go behind the scenes with some leading researchers. Let's dive in.